Convolution will be applied here, and we have discussed about this topic here, the convolution. And in the second step, now we will consider the Fourier series or the Fourier analysis. What is the meaning of this one? Now the signal will be represented in frequency domain in terms of the frequencies. As we have decomposed the signal in the first case as a function of the impulses, in the Fourier series, in this type of the Fourier analysis, here we will consider the different types of the representation. First is, as we know, now the signal may be the power signal or that may be the energy signal. If the signal is periodic, then the periodic signal is said to be the power signal here. And if the signal is periodic, then the signal will be decomposed in terms of the real and complex sinusoids. Means now the signal will be decomposed with the help of the sinusoidal signal. And now these sinusoidal signal either may be real or that may be the complex or a combination of the real and complex sinusoidal. Right? So here, in this approach, we will consider a series. That series is known as the Fourier series. And we have discussed what is the Fourier series. In the Fourier series, the signal is represented with the help of the another functions or the signals, provided these signals or functions are orthogonal to each other. Right? And at the same time, the signal f, suppose the signal is a function ft, then the ft must follow the law of the Dirichlet conditions. That have the three conditions. One is, the first is, it must be finite. The first one is, the signal ft must be finite here. And the second one is, it must have certain maxima and minima in selected range of the time. And the third one is, there must be certain number of the discontinuities having the finite range of the discontinuities in the given time interval or in the given time range. So, if the function follows these laws, then that will be represented with the help of the Fourier series. Now again, the signal may be described into the continuous time and the discrete time. So, if we are applying here the Fourier series for the continuous time signal, then this will be represented as the continuous time Fourier series. And say any function is ft, then ft will be represented as something like in this manner. That is, now this will be represented with the help of the another functions which are orthogonal to each other. Now if we consider here the exponential as a function and the fn is coefficient corresponding to the nth harmonic, then it will be represented as e to power j n omega naught multiplied by t. Here the n omega naught is considered as the fundamental angular frequency. That is, omega naught will be represented as, here the omega naught is nothing, but this will be represented as 2 pi f naught or the 2 pi by t, where the t is the fundamental time period or the time period that has been selected for the periodic function here. And this n will be considered from which range? Minus infinite to plus infinite. And the fn is a Fourier series coefficient, and this will be represented as here the, for the given range, that is 1 by t, integration from minus from that time interval. So here the t naught to say t naught plus t, that is for the given time interval here. And then function itself and e to power minus j n omega naught t. This is the representation of Fourier series in continuous time domain with the help of the mathematics here. That is the mathematical representation here. Now, if the function is discrete time domain, then this will be known as which type of the function? Discrete time Fourier series representation here. Right? Now, how the function will be represented here? As dt. Yes, there will be dt. Right. Here add the dt term. Now we come to this point here that discrete time Fourier series representation of which type of the function? Discretized function, means sampled analog signal. If the signal is sampled or discretized, then how this function will be represented with the help of the Fourier series here. Now the Fourier series for this type of the representation will be something like in this manner, that is the, say the f of the k corresponding to the function is represented as summation for the given time interval. Now say the fundamental time interval here is capital N0. As in this case we have considered in the continuous time domain, we have considered the time period as equal to the capital of the t. Now suppose here we consider the sequences are repeated after a time interval, that is capital N0. So this will be for over this range, that is the N0, and then as we have described in this case here. So here this is the function itself, that is say the small of the fk. What is the ft? After sampling, the t will be represented by the which one? K multiplied by capital Ts. Correct? But the Ts will be the sampling time period. Now, for ease of the simplicity here, we will write this one as the f of the k in place of the f of the kts. Right? So f of the k is nothing but this is a discretized signal corresponding to the f of the t. Now this will be represented by this representation here, that is the a coefficient f of the k and e to the power, as we have described in this case, f of the n. Now this will become the, for the kth sequence here, this will be represented as f of the k, that is the kth harmonic, and e to the power here in the same manner, say the j n omega, say this is the different omega naught, that is one is for the analog and this is for the digital domain, right? Now the n omega naught and t will be replaced by n of the ts, say this is the normalized here and ts is considered as 1, so this will be represented as here the f of the, since we have considered here k, this will be multiplied by k and the t will be replaced by the n of the ts, so this will become the j k omega naught multiplied by the frequency here. As in this case, what is the fundamental frequency multiplied by the number of the harmonics and then t. Similarly here, the fundamental frequency here omega naught multiplied by the harmonics and then multiplied by the time. Time is discretized. Yeah, that is represented in the integer multiple of the ts and it has been normalized here, that is the ts has been considered as 1, so this will become n. Right? Any doubt? So both the equations are represented in the same manner. Now the next step is to find out the f of the k. What is the f of the k here? Over this range, that is which one? The given time interval, that is 1 by n, then summation for this one, that is the n0, and here the function itself f of the kt or the f of the k and e to the power minus of the j k multiplied by omega n into n. Right? So this is the representation of any signal that is said to be the periodic in analog or the continuous time domain as well as in the discrete time domain. That is in analog domain here, right? Analog, that is continuous time and the discrete time with the help of the Fourier series. Now we will come to the point here that if any signal is a energy signal, that is non-periodic signal here, then what will happen? Now the time period will be infinite. In this case, the time period will become infinite. So first we will come to this point here. This is the Fourier series representation of the coefficients. This is known as the Fourier series coefficient here. So in the infinite domain, the Fn will be represented as the function of the omega. That will be a complex function f of the j omega, and this will become, as in this case here, the range, that is the integration, then ft and e to the power minus j omega t d over the total range, that is from minus infinite to the plus infinite. The range of t from minus infinite to the plus infinite. And this is which type of the representation? This is Fourier transformation. That is transform here the function has been transformed in the frequency domain, and this is known as the which type of the transformation? Fourier transformation. And for which type of the signal? Continuous signal. So this will be the CTFT, continuous time Fourier transformation. Right? Now the next is how the ft will be represented. So the ft will be not here the average, that is 1 upon 2 pi, and the range is from minus infinite to the plus infinite f of the j omega and e to the power j omega t, and this will become the d omega, right? So this is the inverse Fourier transformation IFT for the continuous time signal here. Now if we consider here the signal that is discrete, if the signal is discrete here, so we have discussed here the Fourier analysis, that is Fourier series and the Fourier transform. Fourier series for the here the discrete time as well as the discrete time, and here so far we have covered only the Fourier transformation of the continuous time signal. Now we will come to the point here that the transformation of which type of the signal? Discrete time. So this will be more as the discrete time Fourier series representation. As we know, if we consider the Z transformation and Z is replaced by e to power j omega, then we can easily get the Fourier transformation of the discrete time signal, right? So as we know, if any function is xn, any signal is xn here, that is discretized in the time domain, then corresponding transformation in the z domain will become the x of the z, and z will be replaced by e to power 0 omega here, right? In the z domain, that is industrial domain, and this will be equal to how much? The summation of the xn and z to the power n minus of the n, that is e to power j omega, the minus sign and n. And what is the range of the n here? N is minus infinite to the plus infinite, right? This is the representation of any signal xn in which domain? In digital frequency domain, right? Now if we see the function here, then it is a complex. Now this has the two sections, one is the amplitude and the another one is the frequency, and both changes with respect to the frequency. So variation of the amplitude with respect to frequency will be known as the amplitude response, and variation of the phase or the angle with respect to the frequency will be the phase response. And when these two are combined, then we say this is the frequency response of the corresponding signal of the system here, right? So frequency response of this one will be represented by this representation here. Now if we come to the point that we are interested in order to reconstruct the signal, this is here the for the purpose of the analysis, first it will be transformed into the frequency domain, and suppose after processing we are interested in order to reconstruct the signal xn, then how the xn will be reconstructed? Now the xn will be equal to how much? This will become, yes, 1 by n and summation, and this will become the x of the e to power j omega, and here e to power minus plus j omega n, and n will be from minus infinite to the plus infinite, right? Now if we have selected the range for any given time period, that is for a range of the n, that is starting from 0 to how much? N minus 1. Then what will be the range here? At that time this range will become 0 to, yes, n minus 1, right? And similarly here, if the function is described only for this range, that is 0 to n minus 1, then this will be described for this range, that is here the 0 to how much? N minus 1, right? Now suppose e to power, if we see this function e to power j omega n or e to power minus j omega n, what is the nature of this function? This will be the continuous or discrete in nature. What will be the nature of this function? This is, what is the amplitude of this one? 1. The amplitude will remain 1, and the angle, what will be the variation in the angle? How? What is the variation in the angle in this one? 0 to how much? 0 to 2 pi. Yeah, 0 to 2 pi. So the value is changing from 0 to 2 pi with an amplitude of the 1. So this will represent a circle here, right? Now, and this circle is nothing but this will be which type of the representation? This will be continuous representation. And if we consider the minus of the j omega 1, again this will be continuous but in opposite direction, right? Now, what is the meaning of this one? As we are interested in order to consider the signal for which purpose? For which purpose? Filtration or the processing, digital signal processing here. So for the purpose of the processing, and if we are interested in digitally in process the signal digitally, then which type of the signals has to be considered at the input side? Digital. And what is the nature of this one? This is the continuous. So what is the next requirement? This, for the purpose of the processing or the filtration, it has to be converted in discrete form. So here if we have considered this signal, then this signal will be known as the discrete time Fourier transformation. That is Fourier transformation of the discrete signal, and it has to be discretized. That is, the sampling is required here. Now, if the sampling is applied here, then what is the meaning of this one? Now, in place of the omega is continuous, that will be replaced by omega k. K is any integer. That is, in order to select the total range of the omega, now we will consider the integer multiples of the omega. And how these integer multiples will be decided? The total range is 2 pi divided by number of the sequences m, and for the kth sequence this will be multiplied by the k. It means after sampling, here in this equation the omega will be replaced by omega k. So this will become here the x of the e to power j omega k. Omega k means for the discrete values, and we can write this one as the x of the here, right? Now x of the k is nothing but this one summation n is equal to 0 to n minus 1 and e to the power minus j, and then 2 pi by n multiplied by k and then multiplied by n. And what will be the values of the k? K will be again from 0 to n minus 1. Right? Because the total range has been divided into 2n sections. So here the two consecutive sequences or the two consecutive frequencies will be separated by 2 pi by n. Now, if we consider, and this one is known as which type of the transformation? So this is the discrete time Fourier transformation, and this is the discretization of the Fourier transformation. Whatever is the signal, what was the signal? Discrete time signal, and then we have applied the Fourier transformation. Then whatever is the result, that will be known as the Fourier transformed signal, right? And here after sampling means we have discretized the Fourier transformed signal. So this will be known as the which type of the transformation? DFT, that is discretization of Fourier transformation, that is discrete Fourier transformation, DFT, right? Now here we have skipped this one, which one? Xn, yes. The xn function itself will be multiplied by this one. Now in order to compute the IDFT, here the xn, that is in order to reconstruct the signal, this is the process of the discretization. Suppose we have discretized the signal and we have processed the signal. Then after processing, suppose we are interested in order to reconstruct the Sn, then how the Sn will be reconstructed? This will be reconstructed something like in this manner, that is 1 by n summation of the here the x of the k. So the limit of the k will be 0 to n minus 1, and then e to power minus j, it will become plus 2 pi by n multiplied by kn, and here the n is 0 to n minus 1. This is the IDFT. Right? Now, if we come to this point here, that is the computation of the DFT, means the discretization of the discrete time Fourier transform signal here. We just consider this section here. DFT of any discretized signal xn, say xn is any signal, then its DFT is represented something like in this manner, that is n over the range 0 to n minus 1 xn and e to the power minus j 2 pi by n multiplied by kn, and it is defined as the DFT corresponding to this signal, that is x of the k. And similarly, we can define the IDFT, and the IDFT will be the x of the n, that is the IDFT, will become 1 by n, the summation n is equal to 0 to n minus 1, x of the, not n, but here now this will become the k, because this is the x of the k, and e to power j 2 pi by n multiplied by k n. And here we have not described the range of the k, and this k will be from 0 to n minus 1, and here the n will be 0 to n minus 1. So this is the DFT and this is corresponding IDFT. Now if we see these two algorithms or these two procedures, then we will find both are a function of this term, right? That is, in both the cases we have considered a function, that is e to power minus j 2 pi by n. Now we consider the first section here, that is DFT only, and this is nothing but this is a Twiddle factor here. That is, it has a magnitude of the 1, and the variation of the phase is of the 2 pi, 0 to 2 pi, 2 pi to 0. And this may be considered as a Twiddle factor, say W, having a range of the sequences, right? So here e to power minus j 2 pi n, this will be represented by W n. So its power km, this will be represented by W n k n. Now if we consider this function here, the W of the xk, this may be represented something like in this manner, that is the n is equal to 0 to n minus 1 x of the n, and this is W n k n, where the k is 0 to n minus 1. This is the, again we have represented the DFT using the Twiddle factor W here. Any doubt? So, as we know, in order to design or implement any system, we have to consider how many factors? 4 factors. The first is, what is the area? Area on wafer, or the area of the memory size here. And the second one is speed of the algorithm, or the delay corresponding to the algorithm here. And what is the next one? Power consumption, power dissipation, power consumption of the algorithm. And the next, that is the last one, especially it is considered in the case of the DSP, finite word length effect, because we have considered the infinite precision. So when it will be considered in finite domain, certainly there will be some approximation, and due to this approximation the error will take place. That is the depend upon the complexity of the system here, right? And now if we consider this one, this factor here, W n k n, say if we consider the W n k, what is meaning of this one? This looks like something in this manner. Now if we consider the n as equal to 8, so n is equal to 0, then this will be 0. How much? 0, then this will be 1, 2, 3, 4, 5, 6, 7 and 8. So 0, 1, this is 2, 3, 4, 5, 6 7, this is 0 or 8. Right? Now, what are the properties which are associated with this function here? Now, if we see, then we will find that the W and K repeats itself after how many sequences? 8. That is n. So we can say the first property is W and K plus n is nothing but it is same as W and K. This property is known as the which type of property? Periodicity or the periodic property. So this is a periodic property here. Now if we say then W0, this is the amplitude of the W0 and the W4, both have the same value but having how many phase difference? 180. It means if we add here W and K plus n by 2, 4 means 8 by 2, that is W n K plus n by 2, then we will find the same value as equal to W n K but with 180 degree phase difference or the negative sign, and this is known as which property? Symmetry property. Right? So, by exploiting these two properties, we can reduce the complexity of the system, because this system is nothing but in this one we consider the sequence and then it is multiplied by the total factor, then whatever is the result, that one is added to the previous one, right? And if we are in position to reduce the number of the multiplication, it means we have reduced the complexity of the system. And if we follow these, if we exploit these properties here, then certainly we are in position to reduce the number of the multiplications, and hence we can reduce the complexity of the system. This is the DFT, that is the computation of the discrete points, right, corresponding to Fourier transform of the Xn. Now if we incorporate these properties here, then computation will become faster, right? So by the incorporation of these properties, that is if we exploit these properties here, then whatever is the algorithm, that will be known as the fast computation of the DFT, that is fast computation of DFT, and this is known as the fast Fourier transformation. Here this is the Fourier transform signal, DFT is the Fourier transform signal, and we have considered here these properties, then computation is fast, so this will be known as the fast Fourier computation, that is the FFT. Now we will discuss how the FFT will be applied. Means we will discuss the algorithm, the rules and regulations for the computation of the DFT using the fast computation, that is exploiting these properties here, right? I think the time is over.